Hello friends, so this lecture is the last lecture from the integral calculus, and in this lecture I will introduce few applications of multiple integral. So what I will do, first I will introduce the applications of double integral and then I will extend them in case of triple integral. So let us start with double integral. So let R be a region in xy plane, then number 1, if f of xy equals to 1, then the double integral over the region R dx dy gives the area of region R. Number 2, if z equals to f of xy be a surface, then double integral over region R z of dx dy. So what we can do, z is a function of x and y, so we can replace the z with that function f of xy dx dy gives the volume of the region bounded by the surface z and above xy plane. Number 3, if f of xy equals to rho of xy, be the density means mass per unit area. Of the region R, then double integral over R f of xy or rho of xy dx dy gives the total mass of region R. Okay, so if f of xy equals to rho of xy, that is the density function, then x bar equals to 1 upon m, where m is the mass of the region R, double integral over R x times f of xy dx dy and y bar equals to 1 upon m double integral over region R y times f of x y dx dy gives the coordinates of the center of gravity, that is x bar y bar of the mass m in R. If f of x y is rho x y is a density function, then I x equals to double integral over the region R y square f of x y dx dy and I y equals to double integral over R x square f of x y dx dy give the moment of inertia of the mass in R about the x axis. So, this is about x axis and about the y axis, this one. If I0 is Ix plus Iy, then we say that moment of inertia of the mass are about the origin. If I want to find out the moment of inertia about a line, let us say x equals to a, then it will become Ix over R. So, it will remain y square f of x y dx dy and then I y will become R x minus a whole square f of x y dx dy. So, here you can see that this is the moment of inertia about the line x equals to a. If I want to find out the moment of inertia about a line y equals to b, so there will be no change in I y. However, this term will become y minus b whole square. Now, we will take some example based on these formulas which just I have introduced to you. So, the example 1 is the cylinder x square plus z square equals to 1 is cut by the plane x equals to 0, y equals to 0 and y equals to x. So, this is the cylinder. So, this will be the along y axis a cylinder of radius 1 and it is cut by the these three planes x equals to 0, y equals to 0 and y equals to x. Find the volume of the region in first octant. So, let us find the answer of this question. So, it is given that we have to find the volume of the region only in first octant. So, in the first octant the equation of the cylinder can be written as z equals to square root 1 minus x square. Okay. Now, volume is given by the formula z dx dy over a region R. So, the projection of this region, this particular region in the xy plane will be something like this. So, z will be square root 1 minus x square. So, y will be 0 to x, y equals to x and y equals to 0, and in the xy plane where z equals to 0, x will go from 0 to 1, and then dx dy. So, this will become, so only thing I made a dy dx, because these are the limits for x. So, it will become 0 to 1, and then I will integrate this with respect to y. So, y will come. So, it will become x square root 1 minus x square dx. So, let x equals to sin theta, then dx will become cos theta d theta. So, this integral will convert 0 to pi by 2, because when x is 1, theta will become pi by 2, x is sin theta, this will be 1 minus sin square theta cos square theta, square root will be cos theta and cos theta. So, sin theta cos square theta d theta. Okay. So, now I will show you that here for solving this we can use the definition of beta and gamma functions. This I can write 1 by 2 into 2 times this one. Now, this is sin theta. So, this I can write sin theta raised to power 2 into 1 by 2 minus 1, 2 into 1 minus 1, and this I can write cos theta square. So, this I can write cos theta raised to power 2 3 by 2 minus 1. So, by the formula that beta of x y equals to 2 times integral 0 to pi by 2 sin theta raised to power 2x minus 1 into cos theta raised to power 2 minus 1 d theta. The same thing we can see here, x is 1, y is 3 by 2. So, this will become 1 by 2 beta of 1 3 by 2. This will become 1 by 2 gamma 1 gamma 3 by 2 upon gamma m plus 1. So, gamma 5 by 2. This will be 1 by 2 1 by 2 gamma 1 by 2 upon 3 by 2 1 by 2 gamma 1 by 2. So, these two things will be cancelled out. So, answer is 1 by 3. So, in this way we can do this particular example. Another example I am taking here from the center of gravity. So, find the coordinates of the center of gravity of a plate. So, please note here it is a plate. So, 2-dimensional region whose density is constant, let us say k, and is bounded by the curve y equals to x square and y equals to x plus 2. So, the plate is like this, x, y. So, y equals to x square and the other one is y equals to x plus 2. So, it will cut 1 2 1 2. So, the region is this one. So, we have to find out the moment of inertia of this plate when the density is constant. So, it will intersect at this point, which will be minus 1 and 1, and this point will become two and 4. So, first of all, for finding the coordinates of moment of inertia, we need to calculate mass. So, mass will be, let us say, m will become k, let us say density is k, which is a constant, dy dx. Here y lower limit is x square. If I take a this kind of strip, vertical strip, and the upper limit is x plus 2, while the limit for x is minus 1 to 2. So, this will become minus 1 to 2, k I will take out. So, y, so it will become x plus 2 minus x square dx, and this will come out as 9/2 times k. Now, we need to find out the coordinates of center of gravity. So, x bar is given as 1 upon m integral over region R, R is this plate, and then x times density is k dx dy. So, this equals to m is 9/2 k. So, 2 upon 9 k, 1 k is here. So, this k I can take out, again limit will be minus 1 to 2, x square to x plus 2, and then x times dy dx, and this comes out to be 1/2 after solving this. Similarly, y bar is given by 1 by m integral over region R y k dx dy. So, this will be again 2 k upon 9 k minus 1 to 2 x square to x plus 2 y dy dx, and after solving this it will come 8 upon 5. So, hence answer is 1/2 and 8 upon 5. Okay, so, we have taken two examples, one for volume, another one for center of gravity. Now, we will talk about the application of triple integral. Okay, so, in case of triple integral, first of all mass. So, the mass of a region omega. So, now omega is a volumetric region, 3-dimensional region, that is given by the triple integral over the region omega rho xy dx dy dz, where rho xy is the density at a point xy and omega is the region. So, for the application of triple integral, let us take this example. So, find the mass of a uniform solid that is bounded by the region x square plus y square equals to 2x, z equals to square root x square plus y square, and z equals to 0 with the assumption of constant density. Okay, so, let us try to find out the way how to solve this example. So, here I need to find out mass. So, mass will be M equals to the region omega, triple integral over region omega, density let us say that is the constant. So, I will take k and then dx, dy, dz. Now, region is something like that. Z is given equals to 0 to square root of x square plus y square and then a region R, which is given as x square plus y square equals to 2x, and then k times dx, dy, dz. So, z I will take inside. So, dz, dy, dx. Now, the region is given as x square plus y square equals to 2x. So, it means x minus 1 whole square plus y square equals to 1. So, it will be a circle having center at 1 and 0 and having radius 1. So, it will be a circle like this. So, whatever mass we will be having above x axis, the same mass I will be having below. So, what I can do? I can write is 2k. So, k I have taken out, and now I will concentrate on this region only. So, if I change it in polar coordinate, this curve will be r equals to 2a cos theta. So, my radial strip will start from r equals to 0 and it will end on the curve r equals to 2a cos theta, and theta will move from 0 to pi by 2. So, it is 2k 0 to pi by 2 and then 0 to 2a cos theta. So, these are limit for r, these are the limits for theta, and then square root x square plus y square will become r, and dy dx or dx dy will be r dr d theta. So, basically it will become r square dr d theta. So, first solve this one and then you can solve for theta. So, this is the way of handling this particular example. Now, another application of triple integral in terms of center of gravity or center of mass sometime, because both are the same thing. So, center of gravity of a solid is given by the coordinates x bar, y bar, z bar, where x bar is given as 1 upon mass, triple integral over the region V, x times rho x y dx dy dz. Here rho x y is the density. Similarly, for y bar, just replace this x by y, and in z bar just replace this y by z. Okay. So, in this way we can calculate x bar, y bar, z bar, and please note here we need to calculate mass for calculating the center of gravity or center of mass. One more remark I would like to mention here: the center of mass will be about the axis of symmetry if the density is constant. So, this is the example. Find the z coordinates of the center of gravity of the hemisphere of radius a. Okay. So, it is hemisphere, so above xy plane and of radius a, and I need to find out z coordinate of this. So, let us try to do it. So, x square plus y square plus z square equals to a square, and z is greater than equals to 0. Okay. So, basically first of all we need to calculate the mass, and then we will calculate the z coordinate of the center of gravity. So, the idea is mass will be density is constant here, dx, dy, dz. Now, if I use the Cartesian coordinates here, the things will become quite complicated, because z will become 0 to square root of a square minus x square minus y square and so on. So, let us find out the simple way, and we will change it into spherical coordinates. So, spherical coordinates will be x equals to rho sin phi and then rho cos phi, okay. And after that dx, dy, dz will be rho square sin phi d rho d phi d theta. We have seen proved this in some previous lecture, in change of variables lecture. So, hence, and the limit will be theta will go for a sphere 0 to 2 phi, and for the complete sphere phi will go 0 to phi. But since it is an hemisphere, so now my phi will go from 0 to pi by 2. So, mass will become 0 to pi by 2 k times, then I am having 0 to 2 pi, that is for phi, this is for theta, and then r will, because radius is a, so 0 to a dx dy, so rho square sin phi d rho d phi d theta. So, after solving it, sorry, d theta d phi, because we have written integral in this order. So, after solving it, we got it 2 pi k a cube upon 3. Moreover, we need to calculate z coordinates of the center of gravity. So, it is given by 1 over m integral over the region r v omega, sorry, I have taken omega k times z into dx dy. So, again change everything in polar coordinates, sorry, spherical coordinates, and then solve it. So, it will come out as 3a by 2. Similarly, you can calculate the x bar and y bar also. In x bar, here we will be having x, in y bar here we will be having y. The another application of triple integral is moment of inertia. So, the moment of inertia about the x axis is given by Ix equals to triple integral over the region omega y square plus z square into density into dx dy dz. Similarly, moment of inertia about y axis is Iy triple integral over omega x square plus z square into density function dx dy dz. Similarly, the moment of inertia about the z axis is given by Iz triple integral over omega y square plus x square into density function dx dy dz. So, for example, if we are having this one, calculate the moment of inertia of a cylinder, define yx square plus y square equals to 1, z is greater than equals to 0 and z is less than equals to 2. when it is rotated around x axis, y axis and z axis. So, moment of inertia about x axis, Ix is given by, so z is given 0 to 2. Now, x square plus y square equals to 1. So, this is the cylinder of radius 1 along z axis. So, on the xy plane, the projection of this cylinder will be circle of unit radius. So, we can change it into polar coordinates. So, theta will move from 0 to 2 pi and r will move from 0 to 1 rho r square sin square theta plus z square r dr d theta dz. So, we are using here cylindrical coordinates, rho square sin square theta for y and z will be as such density, and dx dy dz will become r dr d theta dz. So, by solving this we will calculate Ix. If I need to calculate Iy, only change will be this sin square theta will become cos square theta, because it will be x square plus z square. So, x will be r cos theta, and if I need to find out Iz will be r square sin square theta plus r square cos square theta. So, r square I will take common. So, it will become rho r square r times dr d theta dz. So, in this way we will solve this particular example. Okay. So, in the brief summary of this lecture, I have introduced the applications of double integral and triple integral. The applications were basically finding the area, finding the volume, finding the mass of a region, finding the coordinates of center of gravity, and then finally finding the moment of inertia about a given line. So, with this I will end this lecture, and thank you very much.